Right, take it off. Anything else? I mean, it's fairly straightforward, the stuff we've been doing, but by the same token, we may have some questions. It's all about propagating waves, right?
Let's see. If you're given a problem, and if it doesn't state whether it's lossless, would you be able to figure out if it's lossless or not?
How do you think, you mean, when you said, can you give me a little more detail?
You're given a E field.
Why don't we do this? So, he's asking a legitimate question. You want time or phase it?
Just start with time domain.
I suppose I give you E, it's a random marker. Literally, I just pulled it out of the cabinet. How much you want to bet this thing survived COVID? This is a brand new marker. And obviously, they don't make them like they used to.
And brought up branding markers once, and they're all useless.
If they've been sitting here since the beginning of COVID, they dry out. I almost feel like going up there and just throwing them all out and say, go order some new ones. But probably in the warehouse, they're COVID markers.
Sitting right next to the pre-COVID hand sanitizer.
COVID wrecked so many things in a way. But by the same token, thank God for Zoom and GoToMeeting and WebEx and all these other things we have, so we don't have to physically be at certain places. I'm gonna, hopefully everybody's here. I want to go through this. This is an excellent question, and I want to tell you this kind of thing, or you may not have even thought of a way to formulate this, but suppose I give you an E field, and this is going to be in the time domain. And say it's equal to 10 cosine of pi times 10 to the 9th t minus, say, I'm just going to leave it as beta x a z volts per meter. All right, when you're looking at this, this is the time domain formulation. Do you all agree? On purpose, I didn't make it. I've kind of, I've got a mixed bag of things. Immediately when looking at this, what do you know omega is, just by inspection? Class? I want you to all take a look at this for a second. Make sure, the question is, if you were asked what omega is, how many know what it is? All right, go ahead.
5 times
10 to the 9th. And this would actually be radians per second, right? Now, if I asked you what F is, what is F?
divided by 2 pi.
Yeah, I know it seems trivial, but trust me, there are people that don't see this. So if I divide that by 2 pi, you get 1/2 times 10 to the 9th, or 5 times 10 to the 8th, and this is hertz, or cycles per second, right? Now, look at this for a second. We're going to make some comments. Is it, don't say anything. Is it lossless or isn't it lossless, and why? Just think. All right, I'm going to put it in the phase domain. If you don't know, this is a great time for you to think. I'm going to go from time to phase. In the phasor domain, now it's usually a vector phasor, but any time you have imaginary numbers, you're in the phasor domain. That's just reality. So the magnitude of the E field would be 10. Then it would be at e to the minus j beta x, right? Why is it minus j?
Because it's a positive x direction.
And it's propagating the positive x direction. Do you all see this, class? And it would be in the AZ direction. All right? Now think of the general form for E in the phasor domain. It's for a propagating wave. It has some magnitude, e to the minus alpha. In this case, it's going in the x direction. E to the minus j beta x, right? AZ. This would be if it's propagating in the positive. What is alpha for us?
0.
Everybody see that? There is no alpha in a sense, but it's zero. If it's zero, now think about what alpha means. Gamma is equal to alpha plus j beta is equal to what? Square root of j omega mu times sigma plus j omega epsilon. Now, if we're not talking about a complex dielectric, if we're talking about just a normal region of space, if alpha is zero, sigma must be zero. If sigma is zero, it is lossless. That's the question you posed. Follow me? Go ahead.
How in this situation do you know that alpha is 0?
All right, I want you to look here for 1 second. Is there any exponential decay? There would be, if it wasn't, there would be an e to the minus alpha, in this case, x. And alpha would have some value other than 0. But if it's 0, e to the 0 is 1, so you don't even bother writing it down.
I mean, alpha is the only like exponential that can be in the time domain form, right? Or like,
It can be a phasor or time.
well,
Because
it's
it's
true. Like you couldn't have beta in your.
Well, you
Not
can't
the
have e to the
exponential,
plus j
right.
beta. No, that you can't have. It's got to, because you see, j does not exist in the time domain. Technically, we could get into an argument. I want to just level with you about this. So when you get into higher level courses in physics and mathematics and engineering, they use an imaginary symbol I or j. That is not something that is visually, you can't observe it, all right? But it's used to identify things like if you talk about, and I hate to do this kind of stuff, but if you talk about stuff where there's a 90-degree phase change with 2 channels in a radar receiver, what they'll normally, even though it's a time domain kind of information, they'll use that J just to identify there's a 90 degrees phase shift in the information here with respect to the information in the other channel. I'm just going to leave it at that. But you can't observe a J. That's a square root of minus 1. It doesn't make any sense. Okay?
So when alpha equals beta, that's the good conductor.
Does everybody understand what he said? Yes. If alpha equaled, for instance, since you're asking this, I want everybody to pay attention. These are great questions. Suppose I give you E is equal to 10 e to the minus 5 x e to the minus j 5 x az. What can you conclude by looking at that?
So good conductor.
Alpha is beta, right? That is only true for a very good conductor. Y'all follow me on this class? These are great questions. I don't know where you got all these, but they're excellent questions. I mean, because these are the things I try to underscore and really make sure kids see, but a lot of times they just don't care. And you need to care about this. Now back to this problem that we talked about right here. I didn't talk about, I'm going to go through a few other permutations. Listen now. All right, so just work with me right there for now. Let me erase this other stuff. Stick with that E field. All right, I'm going to put the 10 cosine, right? This was the original thing I put down. Standard propagating wave, right? When I take a look at this, if I say it's non-magnetic, all right, and I say that epsilon relative is equal to 4. Now, I want you to tell me what beta is. I want you to tell me what the phase velocity is, ny. Now, just do it the way you normally do it. Well, what is beta in general? If we think about gamma, in the most general sense, is alpha plus j beta is equal to the square root of j omega mu times sigma plus j omega epsilon, right? I'm restating what we put down there a second ago. Do you all agree with this? Now, you concluded it is lossless, right? That means this sigma is no longer with us. You agree with that? What does that mean? Alpha is 0, but what? Beta would be equal, or j beta would be equal to what? I got j omega squared, j omega squared, square root of this j omega. You can pull the j out since it occurs in front of the beta here. and you get omega times square root of mu epsilon, right? Now, you all see what I'm doing? Do you see it back there? I want to make sure everybody sees this. All right, now keep watching. Can't I say that beta here would be omega? Do we have omega, class? Yes, omega. And I can say this is really square root of mu naught epsilon naught times square root of mu relative epsilon relative, right? I'm really trying to help you here. All right, really important. C is the speed of light. It's approximately 3 times 10 to the 8th meters per second, and it is equal to what? 1 over the square root of mu naught epsilon naught, right? You agree with that? Can you see it? So I can replace this. I can say beta is equal to omega over c. You see how I have square root of mu naught over epsilon naught? Take a moment. Make sure you see this. If you don't, just ask. Don't feel in any way, shape, or form embarrassed if you don't see something. And then I said it's non-magnetic. What does non-magnetic always mean?
U relative to 1.
Yes, mu relative equals 1, right? If mu relative equals 1, what happens? I have the square root of epsilon relative, right? All right, what's beta for this problem? I'm not done yet. But, so it's what? Pi times 10 to the 9th over c, or 3 times 10 to the 8th, right? And I need the square root of epsilon relative. I said epsilon relative is 4. Square root of 4 is 2. So this would be beta. You agree?
Yeah.
And it would be in radians per meter. Now, next, so that would be beta. You can tell me what that is, but I can see here, I get 10 to the 8th, 10 to the 9th, that's 10 on top. Pi, so it's really 2/3 pi, or really 20 thirds pi radians per second, right? What about the velocity? How do you get the velocity? It's velocity, right?
Omega over beta.
Yeah, you could do omega over beta, right? Really, because it's lossless and it's non-magnetic, I can just say it's c over the square root of epsilon relative, can't I, class? All right, now what do you notice it's going to be? Well, epsilon relative is going to be 4, so I can see this is 3 times 10 to the 8th divided by 2, or 1.5 times 10 to the 8th meters per second. Agree? Not quite done here. Now, what's the wavelength? How do you get wavelength?
Speed of light over the frequency.
Well, speed of light would be nice if it was going the speed of light. It's not going the speed of light, is it? It's
Velocity properties.
Yeah, and really what I want to just mention is this. This is the way I always tell people to think about this. When you're thinking about wavelength, think about in the time domain this argument. Get rid of omega t. Let t be 0. Now, if you were to plot that, you're plotting cosine of minus beta x, right? Versus x. The wavelength is where it repeats itself. Cosine is an even function, so cosine of minus beta x is cosine of beta x. So what is a wavelength when you plot something? It's the distance over which it repeats itself, or the argument is 2 pi change, right? Because that's a cosine function, right? A trigonometric function. So you can say 2 pi is equal to beta times wavelength. This is how you always get it. So beta times the wavelength is 2 pi. This always works for constant frequency there. Therefore, lambda is 2 pi over beta. And that will get you to wavelength every time. Now some people say, well, wavelength is just c over f. That's true in free space. Absolutely true in free space. But we ain't going c. It's the velocity of propagation in this case, because it is lossless. But it would be c over 2, or c over the square root of epsilon relative, right? Divided by f. Follow me, class? You with me on this? And these are real important distinctions. Okay. So did you have another one for me?
I was turning if it was lossless or conductor.
And you know, going from phasor to time phasor is always necessary. So anytime you're doing that, you're always taking a look. If it's in the time domain, you're basically, you note beta, and you note the direction of propagation, right? We can make it complicated. We can have an x and y variable there, or an x, y, and z if we wanted. But in essence, what we're doing is find the direction of propagation, the coefficient in front of those, and I should say in front of the spatial dimension, in this case x. Take that, we know I have e to the minus j beta x, this one. Got a magnitude, right? There is no alpha, and it has an AZ. Now, if that's the E field right here, we can put it in the phasor domain. Why don't we just do this one last time? So the E field in the phasor domain for that one is phasor domain. It's going to be 10, right? And it's going to be e to the minus j. What was beta in 20 thirds pi? 20 thirds pi x, right? And the A z direction, right? So what's a unit vector in the direction of propagation, class?
AX.
Take a moment. Everybody see that? Go with me? AX direction. Right. How do I get H? I want the phasor domain H. Hold up, just wait for a second. Everybody think. I mean, there's people writing down. This is an important point. It's propagating wave. If it's not propagating, then you have to take the curl of E. Remember, if it isn't propagating, you got to take the curl of E and divide it by minus j omega mu to get H, which is a pain. So I don't like doing it. It's propagating. So what do? We say it's 1 over eta. We didn't get eta yet, did we? What's the direction of propagation? AX. We'll get it. We'll get that. And what is it crossed into? E crossed into 10 e to the minus j 20 thirds pi x, right? A z, correct? How do I get eta?
J omega mu.
Hold on, let everybody think for a second. I'm really I'm forcing people to formulate the question. Try to answer it yourself first. Some of you know this very well, I'm sure. All right, how many know it? Okay, at least there's a few people that aren't sure, it looks like. All right. What is eta in general? Always go to the most general form, square root of j omega mu over sigma plus j omega epsilon. Now this is one you have to know. And you really have to know like the back of your hand. Now, what did we concur sigma was, or what would you determine sigma was?
It's lossless, so it's 0.
It's 0. What do you see happening to the j omegas?
Cancel.
Yeah, they go away too. But we're not done yet, right? We have the square root of mu over epsilon. Break it out of square root of mu naught over epsilon naught, right? So say this is equal to square root of mu naught over epsilon naught times the square root of mu relative over epsilon relative. I'm making a point. What is the square root of mu naught over epsilon naught, class? It's, intrinsic impedance of free space are 120 pi ohms. And now you can take it square root of mu relative over epsilon relative. Mu relative is 1, epsilon relative is 4, so it's times 1/2, or it's simply 65. Do you agree with this? Now can anybody do this right here? Take 1 over 60 pi, and then divide that into 10, right? And then we have AX cross AZ is, AX cross AZ is AY, isn't it? So for this one, what do we end up getting? Just magnitude-wise, we got 10 over 60 pi is the magnitude.
What if you minus AY? Because it's going the other way. X, Y, Z.
Well, take a look at this. Let's see if we did something wrong here. Direction of propagation is AX, right? And we have H is AX crossed into AZ would be,
Minus AY.
I'm sorry, minus AY, yes. I'm sorry about this, minus my bad on this one. And it's gonna be e to the minus j 20 pi x, and it would be ay, you're right, but it would be a minus sign in front there, and I circle my minus signs, I'm sorry, absolutely right. But that's how you get it. And I want to tell you that as simple as this seems, people mess this up left and right all the time. Go ahead, Andrew.
So wait, why did you put the minus sign?
All right, think about this. If we have x cross z, normally I tell people to do this. X cross y goes to z and back this way. These are all positive.
Yeah.
In the opposite direction, they're negative.
So it was z cross x.
That was my fault. This time I brought some coffee.
Also for the intrinsic impedance, where did you get the 125 from? Well, I know that's 8 and 9,
That's it.
but
What I did is this. I started with, I had j omega mu over sigma plus j omega epsilon. Sigma was 0.
yeah, so that cancels.
So I have j omega mu over j omega epsilon. The j omegas go. I have mu over epsilon. And therefore I break out square root of mu naught over epsilon naught times square root of mu relative over epsilon relative. And that will always do it for you. But there are a lot of subtleties when you have things that are lossy. Then the velocity can go all over, the impedance, everything, and you got phasor, you got magnitude out of phase. Okay. Another one.
What do you find, if you're talking about a good conductor, or you're gonna have a sigma value that's not given to you, do you just algebraically manipulate one of these
Well, how do you
gamblers?
feel? Can you give me a specific, or you came up with that out of someone? I think. The way you always look at this depends if you're in the phasor domain or time domain. You really want to see what beta and what alpha are. If those are given. Now, obviously, if alpha equals beta, it's a great conductor. If alpha is, say, 1/2 of beta, well, then it's somewhere in between. It's neither a great conductor or a great dielectric. It's lousy at both. But you can figure out from that point, as long as you have alpha and beta, you can get anything you need.
Okay, I think.
You can, if you got alpha and beta, I'm assuming you have omega, then you can get phase velocity is just what, omega over beta, right? You got that. What's wavelength? It's 2 pi over beta, right? You can get any of that stuff that you need, as long as they're propagating. Okay? All right, now,
How would a wave not I don't know if this is weird, but how would a wave not be propagating? I thought there
the
was
term wave implies propagation.
Okay.
An electromagnetic field doesn't have to propagate. You charge a capacitor to a DC voltage, put it in the room. Well, there's an electric field around that capacitor, but it ain't changing with time. It's not propagating. That's it. And some of this stuff, when you're talking about a launched electromagnetic wave, I got to tell you this much. A lot of this stuff, it takes a while to really get appreciation for it. You have basically taken electromagnetic, or you've taken current, and because the charge is being accelerated, you're launching photons that have no mass. Just think about this. No mass, but they have energy and they have momentum. And they're launched, never to come back. All right? Now, there is no change in mass, but the thing is, you're radiating electromagnetic energy all over, and it's never coming back. When you charge a capacitor, all that energy, theoretically, that you put into charging that capacitor, you can pull back out. Can't do that when you launch a wave. And it's one thing, this might be a little far stretch right now for a summer class, but what do you know about electromagnetics in general? Well, the charge, if you think about the attractive force for charges, it's 1 over r squared, isn't it? Q1, Q2, over 4 pi epsilon naught r squared, where r is the distance between them. That is the force of attraction or repulsion. With gravity, what is it for masses? Well, for gravity, it's what? M1, M2 times K, over r squared. Same exact kind of repulsive force. It's a 1 over r squared law for gravity that would be attractive always, right? Now, with gravity, this is the parallel. Remember, when you have a standard type of current and stuff like this in a wire, if it's DC current, nothing is propagated. But if there's charge acceleration, you launch electromagnetic energy. With me on this? With gravity, if you accelerate a star, an acceleration can be like just at a constant radial distance. You know how if you take like a marble or a sinker and put it at the end of a rope and you whip it around, the acceleration on that is going to be equal to, it's really v squared over r, right? The velocity squared over r. There's an acceleration, it's bending that. That launches, theoretically, a gravity wave. Have you heard of gravity waves? The only time they've measured them, supposedly, and this is really a deep dive here, that we go way off, but it's very interesting. In California, they have these long rods that are about a mile long, and let me just say this. So remember with electromagnetic wave, when it's propagating, E and H are perpendicular, right? In the propagation direction. I'm going to try to just make sense of this. So I've got E this way. If it's propagating that way, H this way. When this electric field comes in contact with some free charge, like an a wire, a good conductor has free charge, it will accelerate the charge up and down. And that would be how an antenna works. With a gravity wave, it's very interesting. Remember, the electric field that we're talking about, if we have two charges, the electrostatic forces are either towards each charge or away. But when one accelerates, the electric field that is created is perpendicular to an actual, you might say, between 2 points that are connecting. It no longer is aligned along the actual direction of connection between the two charges. When you're talking about gravity waves, if the charge, boy, it's hard to even talk about this. Suppose I have something that's zooming around this way. It will launch a gravity wave that will have a force vector, as I understand it, that would be in the direction of the acceleration, which is kind of bizarre. And so with these rods, these long rods, they have to find a way. You're a physicist, right? Do you remember these experiments?
I'm not a physicist.
I mean, you took a physics degree, right? The rods themselves, they want to have something. They have these very long rods, and they want to catch something that's going to have a force vector along or perpendicular to the line of the rod to cause deflection. And they measure these extremely small movements. I don't even know how they do that half the time. I think it's laser interferometry. But they detect gravity waves from distant events. And I'm amazed at that because these things, I think it's tough to detect electromagnetic fields from another galaxy. It's even worse. Gravity waves, much, much worse, because it's so much orders of magnitude smaller in terms of the force. I know it's a side, but some of these things keep you interested in what you're doing. When you're watching some of the sci-fi flicks, you'll see stuff like this. Okay, another question for me, or can I? All right, what I want to do now is get back to the actual reflections that I was talking about. All right, and I'll come to polarization in a second, but this stuff's important too. When we're talking about electromagnetic fields coming in contact with surfaces, I define the reflection and transmission coefficient. Do you all remember that? I want to redo that. Didn't I give you a few problems on this? Did you guys do those problems or no? If you didn't do them, you're going to have to be very careful to listen here, because some of this stuff you'll get hurt by. So if I have two regions, I'm going to use air here. Region 1, and at region 2, and assume we have some sigma, some mu, and some epsilon, doesn't matter what they are, and it'll cause us an intrinsic impedance in region 2, which will be square root of j omega mu over sigma plus j omega epsilon. And we're going to assume if we have air, eta is just going to be equal to eta naught, which is equal to 120 pi ohms. But because I want to be consistent with Wentworth's the way Stu Whitworth does this, I'm gonna say it's called A to 1 will be A to naught. Now, last time I showed you this, and I tried to be consistent with the way he did it, he said if this is the z direction, and we assume the wave, the electric field is oriented in the x direction this way, then I can say that the ratio of E incident to E reflected to E incident. And here I better be clear. I'm saying that the incident wave is coming in, and this is the incident wave. And I'm saying the incident wave is equal to some E naught incident. That's just a magnitude. Doesn't matter what it is. And it's going to be, since it's in air, it's lossless, but it doesn't matter what it's in. E to the minus j, I'm just assuming it's lossless, beta 1, in this case it's moving in the z direction, but it's oriented in the ax direction. Now this is Whitworth's convention. If you look at his book, what page is this on? Anybody have your book here?
354.
All right, page 354. Now, that's the incident field. The reflected field is going to have some magnitude, E naught reflected, and it will be E to the plus j beta 1 z ax. Remember, it's going the other direction, right? And there's going to be a transmitted field, and E transmitted is going to be some E naught transmitted, E to the minus j. Now this is important. This is going to have a possibility of beta 2. Right? I mean, it will be beta 2z, but it could have an e to the minus alpha 2z. It could be lossy. Y'all with me? So you have to include that alpha. Do y'all follow me on this class? I'll put down what the coefficients are in a second that actually dictate this, ax. Now follow me on this stuff. So this, the ratio of E naught reflected to E naught incident, is given the symbol reflection coefficient. And that is A to 2. It's always the impedance you're going into minus the impedance you're coming from over the sum of the impedance you're going into plus the impedance you're coming from. This is the reflection coefficient. Do you all remember me talking about this class? In his book, he'll put an R here, I think. But it doesn't matter. The symbol capital gamma implies reflection coefficient in this text and in most. The transmission coefficient is equal to 1 minus gamma r, but, or I should say 1 plus gamma r. It's really probably the best way to do this is simply say it's 2 times a to 2 over a to 2 plus a to 1. Now, I like doing it that way. That's the transmission coefficient. And the transmission coefficient is defined as the ratio of the transmitted electric field in magnitude to the actual incident electric field. With me, class? Now, what about the H field? You remember me putting these down here?
Are those E transmitted, E incident, those the magnitudes of
Yeah.
those?
They're the coefficients. When I say magnitude, they can be negative, so I've got to be careful. See that coefficient there? It could be a negative value, but it is a constant. It's in front of that exponential term. That's the key. So that's really it. Now, in Whitworth's book, the problems I gave you, they're straightforward problems. There's not much to them. But if I did this, and this is the kind of problems I like giving, so I'm going to just show you. Suppose I have this kind of. If I have region 1 is air, and region 2 has epsilon relative is equal to 9, mu relative is equal to 1, and sigma is 0. I'm going to keep this in the z direction. Keep this in the x. Now, follow me on this. And I'm gonna say I have an electromagnetic field incident right here, and it is 10 e to the minus j 50 z ax volts per meter. So I'm giving you that as the incident field. This is a straightforward problem, but at least it'll expose anything you don't understand. Now I want you to tell me the reflected field, more or less. I want you to tell me the actual reflected field's magnitude. I want you to tell me the transmitted field. So I want the electric field transmitted. I want you to just give me that. I want you to give me beta in region 1. I want you to give me omega in region 1. I'm going to ask for beta in region 2. Omega never changes, by the way. It's the same everywhere. The frequency will never change of a wave. Wavelength will change, velocity will change, frequency never changes. Y'all follow me, class? So this is important. I want that, but I want all of it. So the way you start these problems is first get what you need to get right off the bat. Sigma is 0. I know what I'm going to need from those equations. I need eta in both regions, right? Can you all see this, class? Take a moment. Make sure you convince yourself what I'm asking is the way to go about it. First thing you got to get, you got to have eta in both regions. So when I do this, this is air. Eta is just eta naught, and I'm calling that eta 1. And that's 100, I'll put it here. Eta 1 is 120 pi ohms. I hope everybody follows me. Agreed? What is eta in region 2? Well, give me the equation. Start with the fundamental if you don't know. Fundamental is 1. Now notice. J omega mu over sigma plus J omega epsilon, right? What is sigma? I mean, I'm putting it here just so it's the redundancy hopefully will drive it home. You don't want to forget this. So if sigma is 0, it's just equal to the square root of mu over epsilon, right? I'll go ahead and just say, well, okay, square root of mu over epsilon is what? Square root of mu naught over epsilon naught times square root of mu relative over epsilon relative. Square root of mu naught over epsilon naught, class? 120. I'm tired too. 125 times
1/3.
1/3, right? And that's 40 pi ohms, right? It really stuck with that. I had trouble getting through the morning class. Okay? Let's get we got that, we got both. So let's first get the reflection coefficient. Class? So it's 82, 40 pi, hold on, 40 pi minus 120 pi over what? 40 plus 165. Do you agree? What is that?
It's negative 5. Negative 5.
Right? All right, does everybody follow me on this? All right, what is the transmission coefficient? I'll just add 1 to it, right? 1 plus 1 minus a half is 1/2, okay? Now, what is beta in region 1, just by inspection, class?
50.
50. What is omega? Now, think about it now. If you're not forced to think or ask yourself these questions, oftentimes when it's asked, you won't know how to do it. Well, just think about what beta is by definition. In its losses, right? Please take a moment, make sure you're clear on this. So if it is lossless, beta is equal to omega square root of mu epsilon. Right? All right? beta is equal to omega square root of mu naught over epsilon naught times square root of mu relative over epsilon relative, right? I put this there on purpose this way. We're talking about air where it's 50, isn't it? What is mu relative for air?
1.
What is epsilon relative for air?
1.
1. Let's get rid of that. You see this is just omega over c class? With me? Can we get omega? Right? Sure. We have 50, right? Times c is omega. So omega for us is equal to 50 times c. Just leave it like that. You'll see why. Agreed? Now what is beta in region 2? Just look and think about it for a second. I'm doing it very slowly just to make sure. Well, beta in region 2 would be what? It's always, is it lossless? Let's make sure we determine that. If sigma wasn't 0, we can't do this part. Do you follow me? If sigma was something other than 0, then we'd have to use the entire equation for beta, right? We'd have to get alpha and beta. We'd have to get gamma. But for this one, it's just going to be omega times square root of mu naught epsilon naught times square root of mu relative epsilon relative, right? Well, that's omega divided by c times the square root of epsilon relative. And the reason I did it that way is because you can see that mu relative I said was 1, right? Take a moment. Make sure you see this. Everybody with me on this? I'm trying to be clear and not cause any kind of confusion. Now, look. What was omega over beta? 50. See that? Y'all see that, class? So that means, what I'm trying to do is show you. Right there, 50, right? 50. Follow me? You could just plug in 50 right there. You could just say, well, beta in region 2 is just beta in the first region, 50 times the square root of epsilon relative, which is 3, right? So it's 150 radians per meter. So the waveform's changing 3 times as fast in terms of radians per meter. You agree with that? What's the wavelength in region 2? How do you get wavelength? What is it?
2 pi over beta.
Everybody hear? It's always 2 pi over beta. We got beta, we got wavelength. You agree with that?
Are wavelength and beta linked in kind of the same way that omega and frequency are?
Yeah, they're if you have one, you have the other.
Right.
Beta times wavelength is 2 pi. You got beta, you got wavelength. They're inseparable, but it's an inverse proportionality, not directly proportional like omega and f. That's an important difference. With me, class? Not quite. All right, so we can get, by the way, so we got beta, we got that, we got the reflection, got the transmission coefficient. I want to just stick to this one point. Let's go into region 2, and I want to get an equation for the electric field in region 2. Wentworth likes to do this. He just throws out some values and says, all right, come up with an equation. All right, what is going to be the actual transmitted electric field? Well, it would be the transmission coefficient times E naught incident. Do you agree with that, class? Now, it would be times e to the minus j beta 2 times z, the way I've done it, right? And it would be in the AX direction. This would have the units of volts per meter. Does everybody agree with that? Take a moment. All right, let's put the values in. So it says the transmitted field here would be the transmission coefficient, which is 1/2, right? Is it 1/2?
Yeah.
Yeah. So it's 1/2 times what?
10.
Where's my 10, right? Times 10. Now it's times e to the minus j, what beta? 150 times z, right? AX, volts per meter. Agreed? Everybody understand? All right. Now what's the power density in this way? Remember, this is a propagating electromagnetic wave. It has a power density in watts per meter squared. All right? So power density, average power density, P_av would be equal to 1/2, remember, technically it's the real part, of E cross H conjugated. You all remember me doing this? Now, if we have a waveform that's propagating, we can always break this down and say it's equal to 1/2 times the magnitude of the E field, if it's lossless, we don't have to worry about anything else, over the magnitude of eta, that's eta 2, by the way, right here. Then, I mean, it's lossless, or we would have to put e to the minus 2 alpha z. Do you all remember that, class? Remember that? Right? But it's lossless, so we don't need that. And when we have the cosine of the angle that would be there too, associated with eta 2, if it's lossless, that angle is 0. Cosine of 0 is just 1. So it's going to be this, and it would be in the AZ direction, in the direction of propagation. Here, it's 1/2. Now, if you take a look at this just for a second, it's going to be 1/2. And then you could say its magnitude of the transmission coefficient squared times the magnitude of the incident field squared over the magnitude of eta 2 in the AZ direction, and the units would be watts per meter squared. I want you to just follow me on this. I've done it this way for a reason. E here is just for in region 2. This is a transmitted field. Let me put this in region 2 here. So it's really going to be what? It's 1/2 magnitude of the E field. The E field is transmission coefficient times incident field squared, right? Right? Over eta 2 squared. Over eta 2. And this would be it in watts per meter squared, since it's lossless. All right, for our case, what's it going to be? Well, I have 1/2. The transmission coefficient is 1/2, right? Correct? Squared. Now what's this downstairs? Eta 2 was what? 45? Is that right?
Yeah.
Isn't that right, class? Now what's E non-incident? And it would be squared, right? So what's that going to be? Well, I have 100 over 8 over 40 times pi. Agree? That would be, and this is in the AZ direction, so this is the actual transmitted power density. And what would that be actually? That would be 100 over 40 pi times 8. Watts per meter squared. Now, what's the incident power? Or I should say, yeah, what's the incident power density? I'll go back and you'll see my point in 1 second. Okay. I think you got it right there, don't you? What's P average? The incident power density is going to be, and this is for the incident wave, it would be 1/2, right? Magnitude of the E field squared over eta AZ. Do you agree with this? I'm just putting down the general form. I'm going to fill in what the values are in 1 second. Everybody with me, class? So what's this going to be? Well, it's 1/2 10 squared, and this is what? 120 pi. AZ, watts per meter squared. So what's that? 100 over 120 pi times 2, or 245. And we can get a value for that. You agree with that? Now, question. We didn't calculate the value for this, but we could. You agree with that? And here's where just plain old common sense comes in. Erase that drawing, but you take a look at this. If this is region 1 and this is region 2, I know I have an electromagnetic field incident in this region, and I have a transmitted electric field that gets through. I know I have an incident power density, average power density incident on here, and I have a transmitted power density. Right? So power is conserved in terms of whatever power, when I'm talking about a per meter squared thing. So P average input is coming in. This is the amount that gets through. How much is reflected? You don't even need that data.
Incident power minus the.
Right, it would be the incident power density minus the transmit. It's got to be the reflected. Do y'all fall in that? We could get it with the reflection coefficient, but I think this is more obvious, and it's an important little thing to see. Okay? All right, now, in his book, he talks about polarization earlier on, but now I'm going to mention something. Actually, what time do you have?
2:10.
What?
We got like 20 minutes to do this.
We got more than that, probably, but, all right, I'll tell you what, I'll do you a favor. I won't, I'll give you a quiz right now, but here's what I'm gonna do. When we come back on Wednesday, I'm gonna do shielding next. It's a logical thing to do. And then I'll do oblique incidents, come back to the actual polarization. But I need you guys to be here for the next 2 lectures for sure. Some of this stuff gets hairy. It gets a little confusing, especially so I'll do that for you. I got a capitalize or something. It isn't supposed to rain, is it?
I think there's a little chance.
I got this stuff that says